My name is Bill Wells. I'm coordinator for this class this morning. I'm on the Science, Medicine, and Technology Committee for about 3 years, I think. Maybe I'm in my 4th year now, but it's been quite an experience. And what amazes me the most about being a member of HASP is how many well-educated people are also members. And who would want to come and listen to a lecture with a title like this? You're all here. So some announcements first. Please make sure your cell phones are shut off, first of all, and want to welcome the crowd joining via Zoom in the HASP virtual classroom. Special thanks to our course technician, Gloria Goodwin, for supporting our hybrid modality. Membership renewal is out there, and you've probably received some emails or whatever about it. For the year 2023-2024, it's up and running now, so please refer to the HASP happenings, which includes a direct link to the online renewal form. Make sure you select renewing and follow the prompts. Join us for another wonderful year of thought-provoking courses, engaging monthly programs, and exciting trips with HASP friends. If you are in the classroom today and have not yet renewed your membership, feel free to stop by the front desk after class to get it done before you head home. One more thing, tomorrow, Tuesday, July 18th, you are invited to the Summer Sizzle, a fun and social evening reception hosted by the HASP Special Events Committee from 5 p.m. to 8 p.m. at the Outdoor Discovery Center, 4214 56th Street in Holland. All guests are encouraged to RSVP via the link in the HASP happenings and bring a dessert or appetizer to pass. And just a little side story here. I'll be 80 in September, and I have always wished that when I went to a potluck dinner, at least once in my life, there'd be nothing but desserts. It's never happened. So. The wine? Is it wine that he made? Oh, it's his collection, huh? How many bottles does each person get? Oh my goodness. Today's presentation, you can see the title here, presented by Zach Williams. And Zach is different than the rest of us. He actually likes math. He's an assistant professor of physics at Hope College, has a BS from the University of Central Florida, and a PhD in physics from the University of Wisconsin-Madison. His presentation, fusion plasmas and plasma turbulence theory are Williams' primary research interest. So without further ado, Zach.
Well, thanks so much for that introduction, Bill. Thank you for the invitation. Bill saw a presentation that I gave back in March and somehow decided that he wanted to hear more of me talking. So here I am, excited and privileged to be speaking with you all. First, how are we doing on volume? Can everyone hear me? Sounds good? Great, fantastic. Well, thank you all so much for being here. Thank you to those joining online. I think this is the camera that that they're seeing over there. Okay, hello. Thank you for joining us. Yeah, I'm excited to be here. It's amazing to see a summertime classroom full of eager students. I never see a fall-time classroom full of eager students, and it's my full-time job. So this is truly remarkable that you're choosing to be here rather than out on a lake somewhere. So I hope I make it worth your while. So I believe you guys do questions at the end. Personally, I love being interrupted. So if you have a burning question as I'm going along, don't hesitate to throw up your hand or just shout out, and we can have a bit of a dialogue here. That's totally fine by me. So let's dive in. Plasma physics, unleashing the power of the sun. First of all, are any of you familiar with what used to be called sunny delight? this orange drink. I think it came out in the 60s, tasted somewhat like battery acid. And that was kind of their catchphrase, Sunny Delight, Sunny D. Now I think it is Unleashing the Power of the Sun. And I thought that was perfect when thinking about plasma physics. And as we go along, hopefully you'll see the connection to this idea of the sun. What is the sun? What is power that the sun generates? That's what plasma physics really is all about. So let's here. Maybe not. Clicker may have cut off. We're back. All right. Thank you, Ian. So just a little overview of what we're going to be talking about today. So I'll give you a little introduction as to what plasma actually is, and then we'll talk a lot about this idea of fusion energy production, because that's a huge area of study in plasma physics. And that's where most of my expertise lies. So we'll talk about it from an experimental approach, from a theoretical approach, which is more my wheelhouse, and some other deeper physics ideas of turbulence and transport. Then I want to talk just a little bit about the research that is actively happening right here at Hope College with undergraduate students. We are doing theoretical computational plasma physics right here. There's cool stuff going on, so we'll talk a little bit about that, and then we'll wrap things up. But let's first introduce things. When we talk about plasma, first, I want to make it very clear when we're talking about plasma, this has nothing to do with your blood. A lot of people hear the word plasma and they think, oh, okay, so you study medicine, you're doing something. No, nothing with that, totally different plasma. So let's just get that out of the way first. And so as we talk about plasma, it's necessary first to tell you why we care. We'll talk about what a plasma is, but first it's better to motivate it. And so the primary motivator for the field of plasma physics is the pursuit of energy production, novel ways to produce energy, and to produce energy in a sustainable and efficient way. So we have many ways of making energy that we can use. We know we've got fossil fuels, we've got other things that work well in a renewable sense, like solar and hydro and wind. These are, as we try to move societally away from things like fossil fuel and towards renewable energy. Things like solar and wind and hydro are all great, but they're limited in their scope and in their application and in their efficiency. And so there's an ever-present need to improve, to innovate. And so this is where this concept of nuclear fusion comes on to this nuclear energy, and it stands apart amidst solar, hydro, wind, other renewable energy sources, non-fossil fuel-based energy sources, in terms of its, what I would call its potential, the energy density that you can get out of the fuel source. And so where does that come from? For nuclear fusion, this energy source comes from the tiniest bits of us. And there may be some scientists in the room, but I won't assume us all to be scientists. So we are made out of tiny stuff. We are made out of molecules. Molecules are made out of atoms. Atoms are made out of, at their core, and nucleus, and then electrons whizzing around. So what we're going to focus on is that core of the atom, these tiny things that comprise everything that we are, everything that everything in the universe is. And so these core nucleus within an atom, there's a lot of energy held within these nuclei, plural nucleus, nuclei, and this energy under the right circumstances can be unleashed. It turns out if you take these nuclei and you can smash them together under the right conditions, they can combine, they can fuse. We call this nuclear fusion. And in this process, you have a conversion of some little bit of the mass of these nuclei. Some of that mass gets converted to energy. Some very smart patent clerk back in the 20s figured this out. E equals mc squared. Perhaps you've heard of this. Einstein figured out this conversion between mass and energy, and that is where the energy in nuclear fusion comes from. Small amount of mass gives you a big amount of energy. And so what is being shown here is just a cartoon of one such fusion reaction. We have at the top, there are what we call two isotopes of the simplest possible nucleus. hydrogen is the simplest element that we have. This nuclei are made up of themselves things called protons and neutrons. Perhaps you're having good or negative flashbacks of your chemistry classes way back in the day, or not so way back, right? So these protons and neutrons make up a nucleus. Hydrogen just has a single proton, and then different types of hydrogen will have different numbers of nuclei. But anyways, as you smash them together, they can combine to create a new nucleus that has two protons. We'll pose the class. Does anyone know what this nucleus is that has two protons? Helium. So we put two hydrogens together, we get out helium. In the process of doing so, we also release a great deal of energy. This is the energy that we are, in the study of nuclear fusion, attempting to unlock. This is the energy that we hope someday will be supplying power to all of our electrical grids. And this is all very exciting, but this may beg the question, well, okay, what does plasma physics have to do with this? We still don't really know what plasma is. Why are we talking about all of this? So let's get there. If I think about smashing these two hydrogen nuclei together, hydrogen, as I said, is a single proton within the nucleus. Protons have a special property that we refer to as electric charge. If you've ever rubbed your wool socks on the floor on a cold winter day and then grabbed your metal door handle, you've experienced electric charge when you get zapped, a little bit of static shock there. It comes up in a variety of places, but anyways, the important aspect that we want to think about when we think about electric charge is that it can come in two flavors, a positive charge or a negative charge. When we think about electrically charged objects, they interact in different ways. Things that have the same type of charge, like charges, repel. Positive and positive want to get away from each other. Positive and negative will attract. They like to hang out. But the takeaway there is that like charges, positive and positive charges repel. So if I have two protons, two positively charged particles, and these hydrogen nuclei, and I try to bring them together, what's going to happen, class? They will repel. It's hard to get them close enough together to fuse because they don't want to do that. So in order to do that, we have to first inject a lot of energy into the system. Basically, you can just think we are forcing these two things closer and closer together until fusion occurs. And it takes a lot of energy to do that. And so if we're taking our system and we are adding a lot of energy, what happens is that we so-called ionize our system. That means where I may have had, I mentioned atoms are these nuclei, which can have some charge due to protons, and they're surrounded by electrons, which have negative charge. So atoms overall are generally neutral. But when we inject all this energy to smash them together, these atoms get stripped. The electrons fly away from the nucleus, and now instead of what I may have been an electrically neutral gas, I now end up with some electrically ionized mess of stuff. And this is what we call plasma. So if I'm doing fusion, just to recap the idea, if I want to fuse two things, I have to inject a lot of energy. In other words, I have to make it incredibly hot. And so doing, I take what was a neutral gas, like hydrogen, and I electrify it, I ionize it, and now we are dealing with plasma. So there's no way to separate doing nuclear fusion from doing plasma physics. Just to give you an idea of the temperatures that we're talking about here, in order to get this fusion to occur between two hydrogen nuclei, we're working with the scales of 10 million or so Kelvin is the scientific units, but at that large of temperatures, the conversion, you can just say it's many millions of Celsius or Fahrenheit. We're talking about very, very hot temperatures. And so plasmas are very, very hot substances. And now we have a bit of a working definition of plasma, and we're going to be talking about it within the context of nuclear fusion and understanding that, but we can talk just a little bit more about what I mean when I say a plasma. So perhaps you're familiar with the terminology states of matter. I talk about states of matter, solid, liquid, gas. So if I have a solid, like an ice cube, that is a solid state of matter, and I heat it up some, what happens to an ice cube if I heat it up? It melts. Turns into a liquid. So we have another state of matter. It's still the same stuff It's just now less well-ordered structure. Now it's more dispersed. We call that a liquid. If I take my liquid water and I heat it up, I get what? Yeah, it's steam. So again, it's still the same substance as it has always been, just in a different state of matter. So I take my solid, I heat it up, I get a liquid. I take my liquid, I heat it up, I get a gas. If I take my gas and I heat it up enough, we get another phase transition, just like we've gone from solid to liquid, liquid to gas. We keep turning up that knob all the way past 11. Then we go from a gas into this plasma state. We have separated these originally neutral atoms into their component positive and negative charges. It turns out this is not so well known as a smaller subfield within physics, but in terms of what the universe knows, plasma is by far the most abundant state of matter. Over 99% of all what I'll call normal matter, because there's this weird stuff called dark matter that we don't worry about, but of all normal matter within the universe, over 99% of it is in the plasma state. Question?
So this may be a dumb question, but what does it take to maintain plasma in that state of matter? Is there a constant supply of energy that has to be applied, or will it stay there within a certain range of situations?
That's an excellent question. We'll talk about generating and sustaining and confining plasma. If I can pause on, we'll come back to good question and get, yeah, hold me to it. A couple more slides, but excellent question. So yes, plasmas on a universal sense, they're everywhere. Solids, liquids, and gases show up a lot in our everyday lives, but in the grand scheme of the universe, we're pretty small. We see it in, as we'll talk about, fusion reactions, but this is also what you look at when you see the night sky. You look up and you look at all the stars. Every one of those is a big hot ball of plasma. Our sun is just a ball of plasma. So again, the vast majority of our universe is in the plasma state. And within the sun, you know, we walk outside today and it's a little warm and we feel that heat. That heat that we are feeling is generated by nuclear fusion happening at the core of the sun. That's where the sun gets all of its energy. And we say, well, that's really cool. That's a lot of energy. How can we do that same thing here? As we'll see, it's a non-trivial problem to solve. The sun kind of brute forces it. They can sustain and confine these things. They can keep it going because the sun has a lot of mass. In case there's a takeaway, quick, easy science lesson, the sun is big. Didn't know that. It's huge. And so it confines things using gravity. We wouldn't fare too well dealing with the gravity of the sun here on Earth, so we don't want to do it the way the sun does it. So we'll talk about how we can get creative to confine and sustain our plasmas in other ways. I will comment on the fact that while most of this talk will be discussing nuclear fusion, plasma physics, there are other areas of plasma physics in space and astrophysical processes. I'll comment some on the end. That's some of the work that we're currently doing here at Hope, but it's not just nuclear fusion, though that is by and large the most interesting and exciting application for practical purposes. So yeah, that's just a little introduction. Hopefully we have a little bit of an understanding of what plasma physics is. And now we want to turn our focus into talking about plasmas in nuclear fusion. We want fusion to produce energy. How do we make that happen? What does that look like? I will comment a bit though, as I forgot to mention here, we have all these different options for fusion. A fair question that you might ask is, well, what makes fusion so appealing? What makes it so much better than coal or gas or solar or hydro or wind? Well, one of the big awesome things about fusion is the fuel source. So when you think about, if we're using, say, this reaction here, I talked about those hydrogen nuclei that we want to fuse. The one on the left there, the one orange and one gray, that's a special type of hydrogen that we call deuterium. Deuterium is everywhere. Deuterium is very abundant just in the water that we have. I think about 1 part to 10,000 or so. And so I was at the University of Wisconsin before coming here. And so a fun catch line they like to quote for the to give you a sense of the availability of that fuel is that within a glass of water, there's enough deuterium to power the state of Wisconsin for 4 minutes. So when we're talking about nuclear fusion as a fuel source, it would change the world in terms of the ocean is big. We've got plenty of water to work with. So if we can power a state using a glass of water, then imagine what we could do with so much more water. And so it's a very exciting option. You can also talk about the byproducts in a fusion reaction versus we do have existing nuclear fission. Perhaps you've heard of nuclear fission, current nuclear power plants. And that is great. I am a big fan of nuclear fission, but it does have some drawbacks. There are some safety concerns associated with nuclear fission, particularly the products of that. You get very radioactive substances like uranium. Perhaps you've heard of this. Perhaps you've heard of Chernobyl and the messes that can come out of these things. These highly radioactive products are difficult to deal with. They stick around for a long time. We talk about how long it takes for things to decay. Uranium sticks around for billions of years. The primary radioactive product you're dealing with here is another type of hydrogen. We call it tritium. That's the orange dot with 2 gray dots. It has a half-life of about 10 years. So you don't have to worry about the long-term storage. It will decay to safe amounts easily within, not even one lifetime for us. So in many senses, fusion is much more preferable to fission because it's much safer, and the fuel source is much more abundant than something like gas or coal. So this is why we're very excited about it. This is why people are motivated to study it. So let's get into talking about these plasmas. So what does it look like to confine a plasma, to create this reaction and sustain this reaction? So again, plasma, now we're talking about ionized gas. We want fusion to happen with this ionized gas, but we need to put it in it's got to happen somewhere, right? I want to build a lab and I want to create my fusion device. As I said, this is very hot, so I don't want to just stick this in a cardboard box. Wouldn't work very well. The cardboard box would not survive that process. And so the way that we here on Earth deal with this is we make use of a very special thing found throughout nature. It's called magnetic fields. Are we familiar with the concept of magnetic field? Does anyone have a fridge at home? You ever stuck things to your fridge? You use a magnet to stick things to your fridge that it seems to just stick there. There's not tape or anything sticky. There's just this invisible force holding your magnet to your fridge. This invisible force is nothing more than these invisible magnetic field lines. So they work well with certain types of metals, like what you have on your fridge. But they are in general very good at controlling and confining electrically charged particles. And what is the plasma made up of? Electrically charged particles. So magnetic fields are kind of a go-to. We say, well, we don't have the gravity of the sun, thankfully, we would not survive. But if we can create magnetic fields that we can use to confine these electrically charged particles, maybe we can go somewhere. And so you can do, this is some math we do in our intro physics classes. I won't make you work out the math, but there's special type of force that these magnetic fields exert. And the result of working through the math is you find if I have a invisible magnetic field line, charged particles tend to get trapped in a circle winding around the field line. They can move freely along it, but they can't get away from it. They just are wrapped in a circle around it. I think the best visual for this, perhaps this will ring a bell. If you or your kids or your grandkids ever played with these sort of things, you've got these little beads and you can spin it and it'll spin in place and you can flick it and it will move along the track that it is bound to, but it won't fly off that track. It's trapped to the track. And so magnetic field lines do the same sort of thing to charged particles. The beads are like the charged particles. The track is like the magnetic field line. And so they can move along this field line, but they can't depart from it. Not very easily anyways. So people began thinking about this back in the 50s. They're saying, okay, well, magnetic field lines can trap particles very well. So let's create a fusion device, reactor that confines all of these electrically charged particles. Just we have these long magnetic field lines, and it should work great. And so the first fusion devices that were constructed were just these long, basically long cylinders, and they would generate these long magnetic field lines, and they would say, awesome, fusion is easy, and we'll just build this and then we'll get it done. And so that's why we've had fusion power since the 50s. No, it turns out it wasn't that easy, because wall magnetic fields do pretty good at trapping particles around the lines, just like I can flick this particle and it can move along the track. Particles can move along the length of the field line. There's nothing inhibiting that. So they started these reactor devices, and then immediately all the particles along the field lines just run out to the ends. And within microseconds, the discharge it's all hit the ends of the device. And so then you have an engineering problem of how you can sustain the ends of your device against all of this plasma pressure. But that wasn't viable. Once your plasma hits a wall in your device, these charged particles recombine with the particles in the wall. They damage the wall a bit, and then the plasma is neutralized. And so it cools off. You can't sustain your fusion reaction that way. So that wasn't viable, just to do a simple linear device. So they said, okay, well, it's a problem that it runs to the ends. So what if our device has no end? Not to make it a very long one, but what if I take a line and I wrap it around on itself? And instead of having a cylinder, I now have a donut. And so particles can move around as fast as they want. They're just going to spin around in circles in the donut. And this shape, this cylinder bent into a donut, we call this a torus or a toroid. And this is the primary, to this day, the primary model for designing fusion reactors is to use this donut shape. And this is the terminology most commonly used for this is the tokamak, which is a Russian acronym for something. I don't know Russian, but we call it a tokamak, and basically just means a big magnetic donut. And we can use these magnetic donuts to confine plasma. So big win for plasma confinement. We still don't have nuclear fusion today, so obviously that wasn't the end of the story. The fun and tricky thing of doing research and science is that it seems every problem that you solve introduces 10 more. So there's the problem is not yet solved, but that was a big breakthrough, is that this donut sort of shape was needed for this approach to magnetic confinement. So this is by far the most, it's not the only one, but is by far the most popular configuration for fusion plasmas. Have I answered your question to an extent? Okay.
Yeah.
We have a lot more to say, but I'm hoping that this is sort of getting to your. Great question. So yes, you have a basic process of what this looks like. Is you've got your donut, you inject whatever hydrogen gas, and then you apply what is the equivalent to a spark. And this ignites the gas into a plasma. And you have you generate these strong magnetic fields to contain it. So at the core, at the middle of the donut, you have temperatures of 10 million degrees Fahrenheit. At the edge of the donut, you're at room temperature.
Now you've answered it. Thank you.
So this is that plasma, you might think, okay, well, as soon as you lose confinement, are we melting the walls of our device immediately? Because 10 million degrees Fahrenheit is very hot. The key there is that plasma is compared to the density of air, which if you think the number of particles in air is about 10 to the power of 19 particles per cubic meter, whereas within plasmas, it's about 10 million times less. So not very dense. So when they hit the wall, they do damage the walls over time, but it's not a catastrophic, like we don't melt the devices every time that we lose confinement. Otherwise, this research would be very hard. You do have to do maintenance on the walls and replace parts over time, but no, it's not, the wall is room temperature. There's nothing sustaining that temperature. It's all about the magnetic fields that sustain and confine the plasma. How are we doing? Good? Questions? Awesome. Well, let's go forward. So we said that, and this is actually doing a little aside now, just because I think it's really neat. So we've established this idea that magnetic fields are really good at trapping electrically charged particles. And so I had mentioned that another avenue of exploration for plasma physics is the study of space astrophysical settings. And so one big area of this study is looking at the sun and how it interacts with things within the solar system. We call this space plasma physics. And every so often, the sun, there's lots of turbulent chaotic dynamics going on in the sun's atmosphere and under the surface of the sun. And ultimately, those result in the occasional burp. And sometimes the sun burps at us. And it shoots out these plumes of plasma, hot electrical gas, and they come towards the Earth. This could be a big problem. We have these big bubbles or structures of hot electrical gas coming directly at us. Thankfully, we have a built-in shield. The Earth itself generates magnetic fields. This is due to the swirling motion of charged particles in the molten outer core of the Earth. So that stuff is moving and swirling around, and that creates magnetic fields. And these magnetic fields protect us against what we call coronal mass ejections, these solar eruptions or solar flares. These things shoot out from the sun, and these particles get trapped in the Earth's magnetic field lines. So we are protected from them. They get trapped in the Earth's magnetic field lines, and they, much like the beads on the track, they will wind around these field lines, and these field lines congregate at certain points on the Earth, on the magnetic poles of the Earth, which are not identical to, but somewhat close to the geographic poles of the Earth. And as these particles congregate in those locations, they collide with our atmosphere and they create beautiful shows of light. Has anyone ever seen the aurora? Yeah, aurora borealis, aurora australis. These are plasma particles trapped by the Earth's magnetic field colliding with our atmosphere. So there's another area of plasma physics that maybe you didn't know. Anytime you see the auroras, you're actually seeing plasma physics and magnetic field doing work all at once. So that's just a little aside, but I think it's very cool to mention. So back to fusion, we're trying to, we've got our donut with magnetic field. We're trying to confine this electrically charged gas. And the goal is that for this to be a viable source of energy, we know we have to put in some amount of power. We got to give it a spark. We have to ignite it, and that costs some amount of energy. And so then we sustain it, the reaction gets going, it gradually outputs energy. It's only useful to us once we can sustain it long enough for the energy that we get out to exceed the energy that we put in. Otherwise, it's not a very good power source. If we're burning money every time that we try to generate power, then that's just not a very good way to do things. So this idea right here, the energy that you get out should exceed the energy that you put in. That's our goal. I'll later reference the letter Q. This is something you use commonly in fusion plasma physics. We talk about the Q factor. Q greater than 1 means that you've gotten out more energy than you put in. And so that's kind of what we're going for, is sustained Q, sustained and reproducible Q greater than 1. And so I've written little bits of math. I'm not going to go, don't worry, we're not going to go deep into the math there. That's just it's an unspoken rule of giving physics presentations, is you have to put in a little math to show how smart you are. But the basic idea is that even once they figured out the donut of magnetic field lines, the story wasn't over, because you could still have all sorts of chaotic dynamic processes happening within that plasma, within that ionized electrical gas. And via these various processes, you get what is called transport. And basically what this is that plasma that's in the middle of the donut, despite these donut-shaped magnetic field lines being very good at confining plasmas, they're not perfect. And over time, this stuff generally drifts from the core out to the edge via a variety of different processes. And so trying to understand what these processes are, this is the study of transport. A lot of the work that I do is trying to computationally and theoretically understand how transport arises. Specifically, we want to say, well, if I've got these particles confined in the core that are fusing, I want to keep them there. But particles transport out to the edge. Heat that's generated in the core, energy that we contain in there, I want to keep it in there. but it can be lost to the edges. So a study of transport, that is a big part of the work that I do. So when I use the word transport, I'm just meaning we're losing stuff. If transport is happening, we are losing the stuff that allows us to maintain fusion. So how do we study this? First, I'm going to spend a little bit of time talking about experimental methods. I am not an experimentalist, so this is my disclaimer. I started out graduate school in experimental plasma physics and found out very quickly that I'm terrible at building things and working with my hands. I'm much better at the sitting in my office and stroking my beard and saying, and so I let other, more capable people do the experiments and actually build the things, and then I get to just think about it. So, but we'll talk a bit about some of the experimental approaches. And so I mentioned that the donut shape is key, but it turns out there's many different ways that you can build a donut. And so this is not an exhaustive list by any means, but 3 of the big ways that these donut-shaped devices or toroidal fusion devices are created. These are just 3 of them: the tokamak, the reverse field pinch, and the stellarator. And so I'll just briefly discuss each of these. The tokamak is by far the most common type of donut fusion device. And so it's not actually a perfectly, if you picture, you go to Good Time Donuts or whatever place in Holland, you get your donuts. They are, if I cut my donut in half and I look at it, it's a circular shape. You can hopefully picture that with your donut. With the tokamaks in general, it's not actually that shape. It's shaped more like a D. We'll see pictures shortly, but people have done a lot of work for decades trying to optimize the geometry of the donut to figure out what is best for confinement. They found that that D shape actually works the most effectively. As you create these magnetic fields, you can direct them in all sorts of different ways. Again, thinking about a donut is really 2 circles, right? I can go long way around the donut, or I can go short way around the donut. And so your magnetic field lines are some combination of going like this and going like this. How you choose to orient them, how much this way versus this way, differentiates different types of devices. And so the tokamak donut has the field lines going primarily the long way around the donut, whereas the reversed field pinch, which I did a lot of my graduate work on at the University of Wisconsin, is a little more mixed. It's, instead of being dominantly long way, there's parts where it's dominantly the short way, or it's kind of like a corkscrew all around the donut. And these different configurations have their pros and cons. And so they're all worth studying. They all contribute to the growing body of knowledge that we have to inform future device design. And another strange one that's become much more exciting probably in the last 20 years or so, the stellarator. And this is, again, it is sort of like a donut, but they've taken it and they've kind of put kinks as you go around the donut. They put some kinks into it, and that has some very beneficial properties for the confinement. The engineering these is very difficult. So you have to design these, basically what are big wires that you drive electrical current in that create these magnetic fields. It's an impressive engineering feat, and is very difficult and expensive one. So again, all of these have their pros and cons, but the big takeaway from this is that people all around the US, people all around the world are working on fusion devices in many different ways. We don't have the answer yet. So there's many different types of fusion devices that are still actively being studied. We have here, this is a close-up picture of the Madison symmetric course. Again, I only show this because that's where I spent a good portion of my career thus far, was working with MST. Again, this is the reversed field pinch, and you can see, believe it or not, underneath all of that machinery, there is the metal donut buried deep in there. And they can even pull all that stuff back, and they can open up that donut to do maintenance every so often. And it's quite an ordeal. It happens once every few years or so out of necessity, but as you might imagine, it slows things down for a long time. So they want to minimize that. But an impressive array of diagnostic tools and sensors, and Lord knows what else is in there. I certainly don't, but it's not just a physics problem. The problem of fusion is very interdisciplinary. Physics is a big part of it, but there's lots of engineering and material science that goes into building one of these and sustaining one of these. And so I think this nice It's a nice way to visualize just how complicated the machinery that you're dealing with is. So where are we going with this on the experimental side of things? We've been studying fusion, working on running reactions and refining the design for decades. And the next big step, because there's a question I often get when I give these sort of presentations, the next big step is, well, are we getting there? Are we getting close? Are we going to have fusion in 10 years? And the funny but sad statement that I've heard described is that fusion has been 50 years away for 60 years. So we are making progress. It is a hard challenge to address. But the next big step the hope is that this will change the game for fusion plasma physics, is the development of the huge, new and improved tokamak, ITER. Has anyone heard of ITER? Awesome, got one hand, that's great. Well, now you have. So ITER, this is the newest tokamak. So again, it's a huge donut being built in the south of France. So ITER stands for the International Thermonuclear Experimental Reactor. Also happens to be Latin for the way. So this is our hope, is this is the way forward with fusion. This has been talked about for a long time. First conceptualized in maybe late 70s, but definitely by the early 80s, people were talking about this, and they were designing and planning, and this is a collaboration across many different nations, and so things are going to move slowly anyways, but then it's a complicated problem and it's a big investment. So, measure twice, cut once, right? They measured 50 billion times, and we're just now beginning to cut. Question?
You ready for a wacko question?
Yes.
I'm thinking of if this were operational, what it would do for transport through the air. So with all the UFO nonsense, how would this play with that?
So I guess I don't know much about UFOs. I haven't spent much time studying that. I think that as far as the influence it would have on things outside of this facility, if you're worried about like radiation or something, if that's what you're asking about, it's entirely safe in that regard. You mean once we have fusion, or? Yes, as a fuel source. Oh, sky's the limit. I don't know, because really, like, once we get fusion going, fuel will become silly cheap. A glass of water is pretty cheap, right? So I have no idea. It will change the world for sure. Right. So it's not that it's generating a different type of power. In the end, the power is just it's going to be electricity. So I should have clarified that perhaps. So, right, exactly. So we can connect, it will be connected to the power grid in the same way. It turns out that we figured out how to make power, and it's kind of silly. It's like, if we make something hot, it moves. This is your car engine, the pistons or something. If something moves, then we have a generator, we can make electricity. We're not changing that. We're just finding a way better heat source. So I should have clarified that. Yeah, so this is not a different type of power. The electricity is the same. The long-term goal is that you connect a device like this to your power grid, but you generate that electricity for dirt cheap. So thank you for asking it. So it wouldn't be like, oh, this is now a special fuel that lets us go at light speed or something. No, it would be the same sort of power that we can generate now, just far more efficient, far cheaper. Yes, great question. So to give you a bit of perspective on this, it may be hard to see that little orange thing right there. That's a person. So this is enormous. This has been under design for decades. They've been constructing the parts since 2013. And as of the past year or so, the parts have been constructed in different parts of the world. In the past year or so, it's all coming to Cadarache, France. And they're actually starting to put this together. Last I heard, it's been a long saga of delays since the 80s, but last I've heard, they're hoping to complete construction in 2025 and begin operation by the end of that year. That's just the first step It'll be a long way. That doesn't mean boom, we're going to have fusion power in 2025. But it means we're going to start learning new things. Yes.
If fusion hasn't been successful to date with existing tokamaks, what's different about this one? Is it a scaling factor that's going to improve the probability of it working?
Absolutely. Great question. So existing theoretical models for things like transport that I mentioned that make confinement hard, most of them say that confinement improves with two big factors. One is the size of the device. This device is an order of magnitude bigger than anything we've ever built. And two is the strength of the magnetic field. So if we can crank up the magnetic field strength, then the confinement is better. And so this will have sizes that we've never seen before and way stronger magnetic fields. And sometimes those go hand in hand. Just as an engineering consideration, you need size to get strong magnetic field. So absolutely, it's not for nothing that we're not just building this and hoping. But yeah, those are the two big factors of size and magnetic field strength. Now, as I mentioned before, as is often the case with research, you find that for every problem you solve, you discover 10 new ones. And so I think we're going to learn a lot within the first couple of years of operating ITER. I don't think this is telling us that fusion is going to be commercially available and connecting to our power grids within the next 5 years. But the way forward is ITER. We're going to learn a lot from this. The step beyond that, if we hit the goal for ITER being a Q, remember that's the quantity energy in versus energy out. So the goal is to get Q equals 10. That means get 10 times as much energy out as you put in. And so if they can demonstrate that in a reproducible way, you may have heard, those of you that follow Science Journal, some places using different methods have broken Q equals 1. They've generated energy from fusion, but they haven't reproduced it. So the idea is to do it, but do it again. Be able to reliably do it. Then this will inform the construction of what would hopefully be the first power plants, fusion power plants. And so they refer to that as demo. So beyond ITER, the hope would be by the 2050s or so, that pending the success of ITER, that demo would be in production.
I have a very unscientific question to
Excellent.
ask you. In the beginning, we were talking about all the heat that was necessary for this fusion. We have a problem with global warming. What are you going to do with all that heat?
Yeah, great question. So there is a lot of engineering considerations that go into, there's things within tokamaks, there's parts of the tokamaks towards the bottom, they call them diverters. And these are portions of the donut that are designed to be destroyed. Basically, it's like we're going to direct all of the excess into this one location. And so these panels, these are things we don't want to do large scale maintenance on the whole thing all the time, but the diverters are meant to capture all of this excess. And so the heat ideally can be captured in diverters, but there's still engineering and material science questions to be answered about how to do that effectively. But yeah, great question.
Zach, am I correct to think that we're dealing with extremely high temperatures here, but not all that much heat, total BTUs generated?
And that's the other, as I mentioned before, the density of the plasma is very hot, but it's 10 million times less dense than the air. So, I mean, the diverters are still important for directing excess there, but also for that reason, it's not like this is not going to be dumping a ton of ash or anything. One of the primary byproducts of these fusion reactions is effectively water. And so that's another huge advantage of this is it doesn't have the harmful environmental aspects.
Looking at your drawing up there,
Yes.
the torus, the path itself and the D ring, that's just that center little section, isn't it?
Yes. So
Yeah,
that's a great,
yeah.
the tokamak is right here.
Right there, right.
Yes. So there's that D sort of shape I was talking
So
about.
what is the main components of the rest of the structure?
So there's a lot of it I don't know. I know a lot goes into in order to create these strong magnetic fields that ITER will have. There's these coils that have an immense amount of current that flow through them, and those you need to keep cool. So cooling systems alone are a huge. So in some sense, as superconductors are a big part of this conversation. I'm not sure how much of that is going into this design. But I can say that cooling is a big part of the consideration and a big part of the infrastructure needed. Great questions. Other questions? So this will be the next step. This will never be connected to a power grid. It will be used to demonstrate net power output, Q greater than 1. And then pending the success of that, the next one to follow it, which people refer to as demo, hopefully by the 2050s would be connected to a power grid. And that's the hope. Again, we have no idea, and we know we expect to happen when we turn it on, but you don't know what you don't know. And this is scientific exploration.
So if you have this combined plasma running around the tokamak, the assumption is that the temperature is sufficient for the plasma to combine, to fuse and generate heat and produce, what were the products? I forgot.
So for the deuterium tritium fusion, there's the helium, and then there are where the energy actually is released there's lone neutrons moving at incredibly high speeds. And so
Oh, it's in the form of neutrons.
it's in the form of neutrons.
Is
So
that right?
yeah, so then the idea is that the inner wall, so neutrons are another particle, different than I talked about protons, electrons have this electrical charge. Neutrons do not. And so these magnetic fields do nothing to stop them. So they will be generated and then they will fly to the walls. So then the idea is to capture the energy of these neutrons when they hit the wall. And that is the energy that is sent to the power grid.
How do they capture that?
Great question. That's outside of my area. So again, that's where it becomes more the engineering design of, yes, these neutrons have this energy, they hit the wall. How do we use that process? It hits the wall and so it has that energy, delivers that energy to the wall. How do we take that energy and connect it to a wall outlet?
And where does the helium that's produced go?
So that is once it's not, it will stay confined because it still has the electric charge. That stays confined in the plasma. And then once I would assume they direct it to the diverters. Another great question. The downside of getting a presentation from a theorist is I don't think about the practical considerations. So, so that's a great question. I don't know off the top of my head. I know it would be
It almost
sustained, but-
amounts to a contamination of the plasma.
Mhm. So it would, speculating, perhaps it would require occasional maintenance. You don't sustain it indefinitely. You have to shut it down and then purge the contaminants and then restart it.
Oh, there's got to be a
But-
trickier way than that.
Hopefully so. But again, that's
Okay.
beyond my pay grade, but great question. Yes.
What happens to the neutrons as they hit the wall? Do they remain as neutrons? Or is there some other
So they
exotic particle physics going on here?
So they won't be traveling with, if you're thinking about like large
Particle
hadron collider
accelerators,
type of
yeah.
speed. Yeah, so they won't be traveling with that intensity of energy. There you're talking about another 1,000 or more fold factor of energy. So we're not going to be creating. They'll get neutrons are very small, carrying a lot of energy, again, to be figured out how to capture that energy and turn it into a usable form. But yeah, we're not going to be creating obscure particles or black holes. Some people think that these sort of things will create black holes. No, it's not going to happen. So, or a wormhole. Great questions. Apologies, I don't have all the answers, but good things for me to study up on. So this is awesome.
Where the CERN is a huge racetrack,
Mhm.
but it's just accelerating a particle to 8.8 speed of light. And it's going to have a collision.
Mhm.
So they're just looking at the dispersion rate of the results of the collision. They're looking at all the
Right, they're looking at, we smash them
together.
together, what comes
Right.
out of it? Yeah,
So it's a totally different type of acceleration, a different type of a particle accelerator, totally.
absolutely.
So the differences of scale are huge.
Mhm. Right, yeah, so this is, I mean, CERN is miles around underneath the ground in Switzerland, whereas this is, if memory serves, this is ballpark, 100 yards ish. So yes, totally different scale. We're not trying to get things approaching the speed of light. We're just trying to get fusion to happen. Right. I mean, it's something that can be studied. It is, if collisions do have an effect on transport, but yes, that's not what the byproducts of collision. We're not producing they're not colliding so quickly to produce new particles.
Dispersion of the collision is what we're after at CERN.
Mhm.
You're not after that.
No. Great questions. Doing good? Awesome. How am I doing on time? Yep. Okay. Sweet. And then let's keep going. So we'll transition a bit now. That's some overview of the stuff that I don't know. So there's the experimental side of things. So now I want to talk a bit about, so there's people building these devices, conducting experiments, learning things, but it is a multi-pronged approach to studying fusion plasmas and solving this problem. And so I come in more on the side of developing models, theoretical and computational models, to try to describe what's happening. Because you can build an experiment, you can run a discharge and say, okay, this plasma lasted for 10 milliseconds, and here's some measurements of density, but you can't go back and freeze time and look at things. Then the utility in theoretical models is that if we play with the equations in the right way, is that we can describe things at any given moment as to what's going on, and hopefully provide more understanding. And in best case scenarios, it's theoretical modeling in close conversation with the experimental development so that they can work back and forth. So some people build these tokamaks in the lab and they run these experiments. Other people build these tokamaks on their computer. So you can develop a computational model to simulate the dynamics of what's going on inside of a fusion reaction. And so there's many different ways that you can go about doing this. For all the different types of fusion reactors there's that many more types of different mathematical models for describing what's going on. And there's many different problems that people try to address from a computational and theoretical standpoint. But the goal is to say, yes, we can do physics, which is to say we can use mathematical models to develop understanding, to describe specifically what's happening, more so than just saying, well, it broke. Well, we lost confinement. Why do we lose confinement? What improves or inhibits confinement? What factors do we need to consider? This is what we're trying to do. And so how do we do this? As I said, many different ways. So again, I'm going to do the theoretical physics thing and throw math up there and just feel good about myself. This is not a math lecture, so don't worry about what you're throwing up there. But we can take some set of equations. This is a set of magnetohydrodynamics. So there's a fun word for you can throw that around at the cookouts tomorrow and then impress your friends. But this is, you can see, we won't worry about the math, but even just the words tell us one way that plasmas in a theoretical sense are thought about. Hydrodynamics, that's fluids. We think about hydro suggests water, but hydrodynamics in general is just a study of the movement of liquids and gases. And magneto, we throw a magnetic field in there. And then we develop these equations. There's some equations, Navier-Stokes equations. These are things that describe how fluids, how gases and liquids behave. And then there's another set of equations, Maxwell's equations, which describe how electrical properties, electric and magnetic fields behave. You smash them all together, you get this theory of MHD. And this is used quite a bit in describing fusion plasmas. It has its advantages, it has its limitations, but really I like to put it up here because it's a very fun word to say. So this is one existing model. I'll go a little quicker through these because math, but what are the kind of questions, an example of the kind of questions that we are trying to answer when we develop these mathematical models? And one of the big things that we consider that we're trying to understand is the notion of stability. How stable is our plasma? What makes our plasma unstable? If we can understand that, perhaps we can control it. And when we talk about stable, we are saying, how does our plasma respond to wiggles? We call them, a fancy word is perturbations, but basically if we disrupt our system in any way whatsoever, what's the plasma going to do in response? And, a nice conceptual tool for this is, you can picture with me, if you will, a bowl. So you're holding a bowl and then you take a small ball and you set it at the base of your bowl. It's there, it's stationary. We call this equilibrium. Nothing's happening to it. It's happy, it's fine. And then we can introduce a wiggle, a bump, a perturbation, which say I'm going to change the system a bit. Say I take my ball and I push it a little bit inside of my bowl. And then I let go. What's the motion of that ball going to look like? We'll go back and forth, but it will never stray too far away from the base of the bowl. Is everyone following with me? So we call that a stable configuration. It never goes far away from equilibrium. This is great. In contrast to unstable, let's say I take the ball out, I flip my bowl upside down, and then I put the ball on top. If I balance it very well, it can be an equilibrium, it can be perfectly stationary. So that's an equilibrium. But now if I introduce a disturbance, I give it a little push, does it go back? No, it runs away. It will never go back to the top of that bowl. That is an unstable equilibrium. And so plasmas, fusion plasmas, are subject to all sorts of instabilities, things that cause them to run away from their equilibrium, their happy configuration. And then these instabilities produce things like transport that cause the heat and the particles to be unconfined. And so a lot of the mathematical modeling says, okay, if I introduce a wiggle, what instabilities develop? And what sort of factors make those instabilities stronger or weaker? If we can understand these things, maybe we can reduce them. And so that's kind of the underlying question for a lot of theoretical and computational plasma modeling. I showed here, this is one way of doing the models, which models the plasma as basically a fluid with magnetic fields. Another approach is through what's called kinetic theory. It's more complicated, so we won't go too much into it. But you do a bunch of math and you can find out it's much harder, much more accurate. So there's always this balancing act. When you are doing computational and theoretical work, you have to decide, how much accuracy am I willing to sacrifice in the name of computational efficiency? And you don't want to have to do more work than you have to, right? Which maybe isn't the best way to approach it, but also sometimes you only have so many resources. So when we talk about computer simulations, an experiment, you can talk about how much money the infrastructure costs. When doing computer simulations, we talk about how much computation power does it take. So you can run simulations on some number of cores in your computer, and you can run that for some amount of time. So if I run a simulation for 1 hour on one core, we call that 1 CPU hour. That would be the cost. And so these simulations can range from tens to hundreds of thousands of CPU hours. So you may be working on their supercomputers at different locations around the country. And you're running simulations there for days using thousands of CPU cores. And so it's its whole own infrastructure, and it's pretty involved. So kinetic modeling can be quite involved. And so the work that I did, I still do some now with one of the students at Hope College, I did a lot at Wisconsin, is to do a type of kinetic modeling. And then we just throw those out to show you what sort of equations that we were working with that. And we say, oh my God. And then we move on from that because we're not going to dwell on the math. But the idea is that we can answer these questions of transport and stability and confinement, not just by doing experiments, but by developing these computational models. And in some cases, some people just do math by hand. It turns out the amount of math by hand that you can do to describe these systems was mostly done by the 70s. I came onto the scene far too late to get to just do math with pencil and paper. So now we have to rely on computational power to solve these sort of things. So, oh, yes, question.
When you do this modeling, do you assume a pure plasma as opposed to one that's got helium contaminating it too and so forth?
So it depends on what you're looking to study. Absolutely, you can include, we call them impurities. So you can, within like the fluid model, you may model it as a fluid of protons and a fluid of electrons together. You may also introduce some small amount of an impurity fluid or something. You can, but you absolutely can include impurities.
Wow, that's impressive.
Yeah, and there's not only helium, but there's, sometimes the plasma that hits the wall might knock some carbon or boron off of the walls, and then that is an impurity. But yes, you can include those. Everything adds to the computational expense, but it can be done. for
That's
sure.
a fascinating business.
Oh, yeah. Yeah, most definitely. So let's, again, within this theoretical description, we can talk a little bit, again, I throw the equations up there, don't even look at them so much unless you get excited by math like me. But what are the questions? I talked about this notion of stable versus unstable. That's one of the big questions that I like to consider in the research that I do. But I also am very interested in studying for an improvement of fusion, but also just as a physicist and understanding fundamental physics better, I'm interested in studying this notion of turbulence. And this shows up not only in plasmas, but in liquids and gases. Anyone ever flown on a plane? Anyone ever experienced, we were coming into some turbulence and rough air? Yes? Yes. Not fun on a plane, not fun in a fusion plasma. And so when we talk about turbulence, it's hard to define. If you ask any two physicists to define turbulence, you'll get two different answers as to exactly what it is. But to put it as succinctly as I can, basically, when we describe a system with a mathematical model, there are parts of the model that are simple, I call them linear, and there's parts that are very complicated. We call them nonlinear. And so if the world were just governed by linear stuff, linear equations, then all of physics would probably be solved because the linear equations are pretty easy to work with. But pretty much everything, if you want to describe them with any measure of actual accuracy, there are more complicated nonlinear terms at play. And so these nonlinear terms, when you're talking about liquids or gases or plasmas, create what we call turbulence. This is a dynamical state of a system characterized by things like chaotic. It's a stochastic. I hesitate to use I'll use the word random, but some people get really nitpicky about what you mean when you say random, but a very chaotic, random, dynamic configuration for your system in which you have dynamics taking place at a variety of what we call spatial scales. So you can have very little, if we think about flow in a river, or actually let's go simpler. Who likes coffee? Coffee drink. Who likes cream in their coffee? Yeah, absolutely. So you can picture a cup of coffee. If you put cream in it and just kind of let it sit, the cream gradually will kind of spread out on its own, but that takes a long time if I want to get cream throughout my coffee. What do? You stir it. And so what you do is you're adding energy. We say adding energy at the size of the cup. And then that energy causes this cream to get mixed in, not just at the size of the cup, but mixed in throughout all the little parts of your coffee. This is a turbulent mixing process.
You using your river as an example, it's rolling along nice and smooth, runs into some rock. You're going to try and describe the eddies and whirlpools that have happened when it hit the rocks.
Yes, absolutely. So if there's no rock, if it's a smooth flow, not turbulent, we use the word laminar. Yes, but you put a rock in there and then you're looking at the flow just on the other side of that rock. Then you get all sorts of swirls and chaotic dynamics. Exactly. Yes. So it's very difficult to do. And so turbulence has been thought about long before plasma physics was a thing. Fluids and gases also exhibit this. So a sketch from Leonardo da Vinci showing characteristics of turbulence. You've got large swirls and you've got smaller and smaller swirls, all of these things mixing together to make very chaotic dynamics. Here's your smooth flow, and then you put a rock in your stream and you can see where out here the flow is laminar and smooth. Within here, not so the case. And Lewis Fry Richardson put it nicely with this cute little quote: big worlds have little worlds that feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. So cute little quote to try to talk about what turbulence is, how we think about turbulence. And so turbulence, this chaotic dynamical behavior that can occur in plasmas, in general, can be very deleterious, very degrading towards confinement. So you get all of this chaotic behavior that's hard to understand, and that can drive a lot of transport out to the edges. And so a lot of the work that I did at Wisconsin, and I still have a student here working on some of that, is for certain fusion device configurations. We run simulations to see what sort of instabilities are present, what sort of turbulence develops from those instabilities, what sort of transport is caused by those turbulence. So that is not only what I've done, but right here at Hope College, undergraduate students, using supercomputing resources in San Diego. So he types on a screen and he's running simulations 1,000 miles away. That's all happening right here. So that's pretty cool. They're doing these things to better understand what's happening. I won't go into the details of interpreting all of this, but suffice to say, that's really cool. I think that we have these sort of opportunities right here in Holland, Michigan. I do want to leave some time for discussion and questions, so I'll briefly talk a little bit about some of the other stuff that's going on right here at Hope. So again, my primary experience is in fusion, but since arriving at Hope, so I started here in 2019, I've been interested in branching out some as a plasma physicist and doing some work on the other side of plasma physics, which is connected to space plasma physics and astrophysical processes. And so I have two other students, and they're working on computational models to describe different plasma processes, not in the context of nuclear fusion, but in the context of stars, namely our sun or other stars, processes that occur there. So just kind of side by side, I have one student working on each of these topics. One of them deals with this notion of convection, which is just to say swirly motion that arises within fluids that have some difference in temperature. If I have a hot surface and a cool surface, we can get swirly motion that develops, and this can transport heat. The sun has a layer in which convection occurs. So the sun has fusion happening at its core, and then the energy produced there radiates out to a certain point within the core, but then the sun gets, there's too many interactions, these photons can't easily radiate any further. And so then the energy that they generate results in convection. We have what's called a convection zone within the sun, and that transports energy to the surface. So I have shown here, this is just a cartoon diagram showing, so I've got hot fluid rising, and then it cools at the outer surface, and then it sinks back down. We call this, and so these circular cells that develop, we call convection cells. And you can see evidence of this. Apologies for the image quality, doesn't show up so great here, but this is an image of the surface of the sun. And you can see there's these little blobs all around, separated by black boundaries. So what's happening is the middle of these blobs is hot fluid coming out, and then those black edges around each of those little cells is cool fluid going back down. And so it's just circulating convection. And so this is a classic problem in fluid dynamics, and there is some work being done extending it to plasma physics, and we're trying to study that here, again, using theoretical and computational tools. Another thing that we're studying is the process of magnetic reconnection. And so I talked about how electrically charged particles get trapped in magnetic field lines. And so whatever happens to the magnetic field lines happens to the particles that they are confining. And sometimes these magnetic field lines, they behave in weird ways. They almost behave in rubber band-like ways under the right circumstances. And so actually, by consequence of convection occurring underneath the sun's surface, all this swirling and rotating can cause magnetic field lines to poke through the surface of the sun, and they can come out kind of twisted and kinked up, and then they sometimes snap, kind of like a rubber band snaps. And we call this process where they snap, certain magnetic field lines cancel each other out. We call this magnetic reconnection, and the snapping shoots things off from the sun. I mentioned earlier this idea of the sun burping. Magnetic reconnection is what causes the sun to burp at us. And so this is another process that we're interested in studying. Again, we do math. This is something Hope College undergraduate students right now, they should be at work. They're working for me this summer, and so I haven't checked in with them more this morning, but they should right now be working with these equations to model these processes. They get paid, but they did sign up, yes. And these models are mathematically complicated. So what specifically are we looking at here? These plots this is data that my students have generated this summer, right here at Hope College. But we're trying to study these very complex plasma dynamical processes. This is where I put on my very theorist hat and stepped very far away from reality, because what we're doing is we're pursuing different mathematical models that try to look at these systems, which are incredibly complex. The equations are very difficult to solve, but can we take them and distill them down to fundamental parts? Can we make them simpler? Or when people solve these full equations, they might be looking at way more than they need to. And so it's almost like a philosophical approach that we're taking. Can we find simplicity amidst this complexity? And we have some promising results. It's still all very preliminary, but we're hoping to go to a conference this fall to present what we have. And I could have given a whole nother hour-long seminar just on this sort of work, so perhaps I'll come back and do so. But for the sake of today, I'll just say this is ongoing stuff. We're really excited about it. We're having a lot of fun. But I think that will be a good place for us to wrap up. What have we learned? Hopefully something. I've talked for a lot. I don't know what you've learned. Hopefully you retain a little bit of this, but we have these ideas of plasmas, these hot electrical gases that under the right circumstances, you can generate nuclear fusion, which may change the world in terms of its ability to produce energy. This is being studied experimentally and computationally. We've got large-scale computing. We've got the development of these devices happening all over the country, all over the world, all working towards this common goal. There's a lot that has been learned. There's a lot yet still to be learned. The processes are complicated. We've got to deal with instabilities. We've got to deal with turbulence. We've got to deal with transport. It's a hard problem, but I think it's one worth investigating and one that can be solved. So yeah, it's been fun. Thank you for great questions. Thank you for listening. Yeah, I've had a great time.
Are there any other questions? There's one was. Louis has a question.
You alluded to what I believe was a British experiment that was reported recently, that they achieved fusion for a very short period of time. I don't know if they've published, reported what they think they may be doing next to improve. I forget what the duration of that was. I forgot it was microseconds or a millisecond. But can you give us more information about what they're going to do next?
I know what you're referring to. There's actually been a couple places. There's also been a place out in Lawrence Livermore, where they using a totally different method. So some people do fusion by just shooting lasers in a very concentrated way and creating fusion that way. And they also report Q greater than 1. So a couple people have made this claim, but it has not been published because they can't reproduce it. It's been advertised, but as far as what they're going to do to try to reproduce it, your guess is as good as mine. I haven't heard much on that, and I just know like there was a lot of buzz and excitement about it, and you have to approach science with a little bit of cynicism, because doing things once, sadly, is not that's not science. Science has to be reproducible, and so I'm hopeful. That'd be amazing, but I don't know what direction they're going with at this point. Yeah.
At one time, the company that made the Cray computer was known as the supercomputer. Have they become obsolete, replaced by yet another generation made by some other company?
There are many. I have worked on some computers with Cray architecture. So I wouldn't say they're obsolete, but I wouldn't say they're the only out there. There's many, and there's all over the country now. There's many different supercomputing facilities. So I don't know if you're familiar with Moore's law, but basically the improvement in technology like doubles on itself every 2 years. And so 18 months is, yeah. So it's crazy how quickly things become outdated in the world of supercomputing, because it still moves very quickly. Yeah.
I have a general question about computational modeling.
Yes.
How, in, a minute or less, can you generally describe how you develop and prove a computational model?
Yeah. So it always starts from a theoretical model. We have a set of equations that says, here's how the system works.
Okay.
As I said, the ability to solve those equations for any scenarios by hand has been done for 30 plus years. So now we try to solve more physically realistic, more accurate scenarios. We can't do those by hand. And so we can take these equations and we can effectively feed them into the computer. How you translate equations into computer language is a whole different discussion, but you can do that. And you say, all right, now you solve the equations because I can't do it anymore.
Okay.
And that's effectively what it is. You're still just doing math, but the computers can do it way faster.
Got it. So at some point, somebody needs to say, okay, here are the models.
Yes.
Whether they're purely theoretical or theoretical that has really been taken to another extreme by supercomputing, right?
Yeah, absolutely. So it's
Yeah.
always still us giving it an equation.
Yeah, somebody
set of
has to go
equations.
out there and tie that into a beaker, right? And say, okay, we've got, all kinds of perturbations and blah, 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 blah. And do they match these models? And
Right.
does this model match the new? So what would you call this? Would this be?
So if you're asking, connecting the models to reality.
Yeah.
So that's a big part. As I mentioned, the best computational theoretical work is done in conjunction with experiments.
Okay.
And
you.
so a theoretical or computational model is worthless until it can make a testable prediction. I can sit here all day and do math and say, look at this cool stuff that doesn't have any testable conclusions. If I can't say, well, under these conditions, the amount of transfer that you'll see is this, then the experiment goes and says, oh, we did those conditions and we saw that. Then we say the model is good. Now we have an understanding. But if I can't make a prediction that they can observe, then it's just a model. We can't give it any credence.
Computational modeling and the experimental folks, are they able to work together enough to make progress?
Yes, I would say, at least in my experience, I would absolutely say so. And I think there are categories for funding. And so, a big instrumentation grant is not going to be competing for funding with oftentimes computational, in terms of money, computation is cheap. I don't need a big fancy lab. I need a computer. And so I apply for, I don't need $100,000 to do research. I need 10 million computing hours. And so I apply for that rather than for the funds that they might need.
We do have a question from the chat.
Oh, yeah.
Russell asks, how quickly can the next tokamak machine be built?
So smaller scale machines can be built within a matter of a few years. I would say ITER is a whole different animal, in part because it's many different countries working together. And so that slows things down a lot. There's a lot being invested. The overall amount of money that has been put into ITER is tens of billions of dollars. And so you have to spend a lot of time making sure that the money you're investing is going to work. You know, you, like I said, measure many times, cut once. And so there, ITER stands apart as taking so long. There's been, in just the past 10 years, there's been a bigger push towards private sector development of fusion technologies. And so Commonwealth Fusion Systems over in Boston, they work closely with MIT, and they are in the process of putting together a small tokamak that, yeah, within 10 years time will come from not existing to being operational. So when it's just one company working by themselves and not having to collaborate, and it's a much smaller scale, then it's much easier to get done fast. ITER's just massive in every possible rubric. So that's what's made it take so long.
On the subject of experiment and theory, just as theory needs experiment to substantiate a result, experiment needs theory to explain what happened.
Absolutely.
So those two go together. You can't have one without the other.
Absolutely.
And that's called the model, the scientific method.
Yeah.
And it works.
Yeah, it absolutely does. A lot of my graduate work, like I said, I worked with the Madison symmetric torus, and I was down the hall from the experimentalists. And so they would run these experiments, and then they would say, we have this data, we saw these fluctuations, there were these profiles, like what's going on? Because you can't look at experimental data and say, oh yes, this is the instability that we saw. The reason that the transport was this level was because we had this sort of turbulent behavior. They can measure real things, which is great, but that's the reason for computation in theory, is that we can take a deeper dive. I can simulate things and I can press pause. You can't pause a fusion reaction, but you can pause a simulation. You can say, all right, at this moment in time, I see these sort of things going on. And so it's absolutely, yes, the back and forth is science at its best.
The mathematics behind turbulence, for example, are you limited in the questions you can ask by the computer power you have available?
Am I personally?
Yes.
Yes. Yes. So in the process, I will, over the course of August, be writing a grant for computing hours to help us expand that. We did last summer. We built not a supercomputer, a small 64 core computer, so that we can run not nothing, but we can run some small scale stuff. But as the research progresses, we're finding more and more the need for supercomputing resources beyond what we can just build with our own hands. So
I think you mentioned you worked with a computer in San Diego.
yeah, so I have one student who is actively doing that. That went well. So this summer he used 400,000 CPU hours on the simulations that he did. And so from that, my plan is in August to apply for another 1.5 million. So
Are there any other questions? Well, Zach, I'd like to thank you for the timing has been
so much
perfect
for
here.
coming. It's fun.
Each of us will probably think of 3 or 4 more questions when it's over. So
Well, I
thank you
work on
again.
campus. You can look me up. My email is on the Hope website. So anytime.